Continuing with the three-phase transformer connection, we will discuss today star delta and delta star connection. In Y delta arrangement of a single phase transformer, which is used for a three-phase connection, is often found at the receiving end of the transmission line, because we know that here in the case of the delta connection, that is secondary in the case of star delta connection. Suppose if you are connecting the phase voltage of 230 volts, for example, if you are taking 230 volts in the primary side per phase voltage, the second side, if it is considering 1:1 transformer, the secondary, the voltage is also across the each winding is 230. However, the line voltage in the star connection, if all the three transformers are connected in star connection, in that case you are getting the line voltage of 230 into root 3. However, if you are switching over to the secondary side, which is a delta connection, the phase voltage is 230 volts as well as the line voltage is also 230 volts. Means from the primary of 230 into root 3 is changing to 230 volts. There is a voltage drop in the voltage, means there is a step down of the voltage. That is why wherever there is a stepping down the voltage from high voltage to low voltage, in that connection we are using the star delta connection. That is why Y delta arrangement of a single transformer is often found at the receiving end of the transmission line. The reason, that is why is given, that is the ratio is what we are getting here is, the reason is that it provides a large step down voltage ratio from primary phase voltage side to the secondary phase voltage. It follows that the ratio of the line voltage from secondary to the primary voltage is 1 by root 3 times K. That what I am told you is that in the secondary, that is a V2, the voltage is V2 only, that is the phase voltage is equal to line voltage, whereas in the primary it is root 3 times V1, that is V2 by V1, what we are getting is 1 by root 3 times K. Therefore, there is the transformation ratio is 1 by root 3, means you are getting the less than the 1 value, so that you can step down the voltage from high voltage to low voltage by the ratio 1 by root 3. Correspondingly, the ratio of the primary line current to the secondary line current is 1 by root 3. But in the case of the transformer current ratio, that is I1 by I2. I1 is the primary voltage. There it is star connection, that is the line current is equal to phase current. Therefore, I1 is equal to I1 only, the line current. Whereas in the secondary, the line current is root 3 times I2. I2 is the phase current in the secondary. Therefore, its line current is root 3 times I2. Therefore, ratio is I1 by I2. That is I1 divided by root 3 times I2. Therefore, here also the transformation ratio is 1 by root 3 times the K. That is the corresponding ratio, the ratio of the primary line current to the secondary line current is also 1 by root 3. At the same time, we are getting there is a phase shift of either 30-degree lead or lag in the case of star delta transformer. That we will see in the connection diagram and the phasor diagram. It is star delta transformer, means the primary of the three transformers are connected in star, so that either end connection of each phase is connected to a common point, that become a star point, and from the remaining terminals you are inputting the voltage, that is a star connection. In the delta connection, what you are doing, the end of the first is connected to start of the first, end of the second is connected to start of the third, and end of the third is connected to start of the first, so that we are getting a delta connected. From that you are tapping the three phases A, B, C. That we will see here. I am considering here there are two possibilities of connecting the delta. There is one, the combination is, that is A1, B2, B1, C2, C1, A2. What do you mean by that? I will show you in the help of the diagram. This is one way of connecting the delta connection. How exactly you can see here. There are three transformer. Then each of the terminals is marked as, it is the first transformer, It is A2 A1. It is a primary side, and A1 A2 is the secondary side. Here B1 B2 is the primary side of the second transformer. B1 B2 small at the secondary end. Similarly, we have got C1 C2 and C1 C2 of the third transformer. The delta connection, first we have to do the star connection, means all the end, that is A1, B1 and C1 are shorted, so that it is become a star point. Therefore, from the remaining three terminals, that is A, B, C, you are inputting the voltage here. This is the input voltage you are giving. This is become a star connection. In the delta connection, what I told you, that is end of this is connected to start of this. End of the second one is connected to start of the third, and end of the third is connected to start of the first. This is a combination, one combination. That is, I told you it is A1 B2. That is A1 B2, B1 C2, B1 C2, then C1 A2, C1 A2. That is from C1 to A2. That connection I am making for a delta connection here. Therefore, A1 B2, B1 C2, C1 A2. This is a delta connection. This is a star and delta connected winding. Now we have got output terminals A, B and the C. Then we look into the vector diagram for this particular connection with respect to the primary and secondary. How exactly this looks like. I have got A1, A2, that is a voltage across the first transformer of the primary side. Then the voltage across the primary side of the second transformer lags the first by an angle of 120. Therefore, it is V1 V2, and the voltage across the third transformer lags the second transformer by 120. That is C1 C2. Then here it is connected, that is across A1 and A2 of the secondary, depending upon the transformation ratio, you are getting the voltage across A1 and A2, B1 and B2, C1 and C2. In this case, the line voltage is same as phase voltage. In this case, the phase voltage is across A1 A2, B1 B2, C1 C2, whereas your line voltage is between A to B, B to C, C to A, which is root 3 times this phase voltage. Root 3 times this phase voltage. Okay. Look into the here. I got a secondary voltage across the first transformer is A1 and A2, that is in phase with this. Just I am bringing here, that is A1 A2, and drawing for the secondary. That is, the voltage is in phase with A1 A2 of the primary. Similarly, the lowercase b1 b2 is in phase with b1 b2 of the primary. Therefore, I am adding here because my connection is A1 B2. You can see here it is A1 B2. Therefore, it is A1 B2 here connection. Just I am beginning parallel. I am putting as for this connection, that is A1 B2. Then I have got a vector, that is C1 C2 of the secondary, that I am bringing. I am putting here. Can look into that connection, that is it is a B1 C2, therefore it is B1 C2, and here C1 A2. This is a connection here. In this case, once again the same diagram I have drawn here, that is A2 B2 C2, it is A2 B2 C2, and this also I am making as A2 B2 and C2, this is A2 B2 C2. Then this is a your neutral point. We can look into here, there is a lag of the 30 degree, that is the neutral is lagging shifted by minus 30 degree, that is lagging shifting of a neutral of 30 degree, that is in the case of one type of connection, that is A1 B2, B1 C2 and C1 A2. Then you will look into the possibility of connection of the delta connection in the secondary. The second the possibility of connecting the delta is A1 C2, B1 A2, C1 B2. How we are connecting this using the delta connection in the secondary. Just you have to look into. Just for this connection, what you have to do is just you have to shift these two transformers. You have to interchange their transformer. then B to C, C to B. Just you have to look into, just you have to observe the change in the connection. That is, now the sequence will becomes, previously it is A, B, C, that is sequence. Now it is sequence for the next connection is, it is AC, the ACB, that is ACB, that is what I am getting here, that is ACB, ACB. That we'll see how exactly we are connecting here. See here, I am replacing this transformer here. Then the corresponding terminal is now C. This is C. Now it is C. This I am changing into the B. Okay. Subsequently, here I have what? This is C. This is C. Then these terminals are, now it is A1. A1 as it is the first transformer. Here it is C2 C1. Now I am replacing this transformer now by the B transformer. Now my terminals are, here it is C1 C1 and here is what? B2 B2 and C2. Just what I am replacing is replacing B by C, then C by B. Then I am making the once again the star connection. All end of A1, C1 and B1 are short circuited and inputting at ACB. Now the secondary is, now you have to look into the secondary connection. That is A1 is connected to C2, that is A1 C2 connection, what I mean. Then C1 B2, that is C1 B2 here, C1 B2. Then B1 A2, B1 it is A2. This is a connection. For this, what is my phase sequence here? It is ACB, therefore it is, here it is A, that is voltage across this. This is C, then the third one is B, that is primary side. The corresponding, you can shift here as A, this as a B here, then this as a C here. In this case, if the neutral is shifted 30 degree, that is a leading shifting of a neutral here for the connection of ACB. ACB means, what I mean is, when if you are connecting in the star to delta, then there is a phase shift of 30 degree. Okay. Some of the salient features of the star connection we look into. This type of transformer, I told you, is used principally where the voltage is to be stepped down, as for example at the end of the transmission line, that is the distribution purpose. In this type of connection of the transformer, neutral of the primary winding is earth, that is the primary winding is star connected, it can be earth. In this system, the line voltage ratio is 1 by root 3. That also is seen. That is the current ratio as well as the voltage ratio is 1 by root 3 times of the transformer turns ratio. That is the voltage and current ratio is the 1 by root 3 times the transformation ratio, that is the turns ratio. And secondary line voltage have a phase shift of plus or minus 30 degree, that we are seeing with respect to the primary line voltages. On the high voltage side of the transformer, insulation is stressed only to the extent of 57.7%, because in the secondary we have got a delta connection, means it is the phase voltage is equal to line voltage. Therefore, the truss on the primary winding to get the same delta connected line voltage in the primary side, then it is very less loading on the primary winding, that is star connection, that is around 57.7% of the line voltage, and therefore there is some saving in the cost of insulation in the primary side. If you are going for star delta connection transformer, there is a saving of the insulation in the star connected side. The next session we will look into the delta star connection.